Tube amps sure are sexy. They're kind of intimidating too. Welcome to Lancaster Hi-Fi. If you're new to my channel, I'm glad to have you watching. This channel is small but growing. It hit 1,000 subscribers a year ago, and now I'm closing in on 5,000. If you enjoy the video, I hope you'll watch some of my others and subscribe to the channel. If you're a returning viewer, what are you waiting for? Subscribe, please. So tube amps are sexy, but they're kind of intimidating. Whether because of hot glass, dangerously high voltages, high cost, concerns over adequate power, sheer mass, or just that tube amps are just too much trouble, maybe you haven't seriously considered purchasing a tube amp. I get it. But I'll tell you this. If you haven't spent serious listening time with a good tube amp, you're missing out on something special. If you stayed away from tube amps, at least in part, because you lack basic knowledge, then this video might be a good place to start. In this video, I'll go over some tube amp basics, introduce the two most common types of tube amps, and review the pros and cons of those types. I'm going to focus on hi-fi tube amps, but most of what I'll talk about is relevant to guitar amps as well. I'm also going to focus on power amps, because I know the most about those, and it's with power amps that we can draw the greatest distinctions. Before I get into it, I'll briefly address what should probably be your first question. Do tube amps really sound better than solid state? I don't know. I mean, I think so, and I have done some A/B comparisons and found myself and others favoring the tubes. But just like solid state, tubes can be poorly implemented. Tube amps come in two basic flavors, single-ended and push-pull. Just as importantly, tubes come in two basic flavors, low-power preamp type tubes and high-power output type tubes, plus rectifier tubes, but let's leave those out of the discussion for now. The terms single-ended and push-pull refer to the use of the high-power output tubes. Okay, I'm going to sketch these types of output stage in a way that's easy to understand. It's not the way tube amp circuits are often drawn. In my drawings, signal will come in on the left and go out on the right. Highest voltage will be at the top and lowest at the bottom. Okay, here's our one tube that we need for one channel of the single-ended output. We apply signal here at the grid. If you know transistors, that's like the base. If you know FETs, the grid is like the gate. At the top of the tube is the anode or plate, and that's where we put high voltage. But we do it through this coil or winding. Lots of wire here, high voltage here. At the bottom is the cathode or cathode. That we connect to ground through a resistor. With current flowing from high voltage at the top through the tube to ground at the bottom, the resistor holds the voltage on the cathode up at something like 10 or 20 volts. That's good because we need the grid to be at a lower voltage than the cathode for the tube to work right. The value of the resistor is chosen to get the right voltage at the cathode and the right current through the tube. By choosing the resistor, we're setting the bias of the tube. And this method of setting the bias is known as cathode bias, or sometimes automatic bias. We could also directly ground the cathode if we put the grid at a negative voltage. And that method of biasing the tube is known as grid bias or fixed bias. I know, I'm getting out into the weeds a bit here, but you'll hear these terms thrown around. In summary, when you hear cathode bias or auto bias, think big hunking resistor between the tube's cathode and ground, and the grid at 0 volts. When you hear grid bias or fixed bias, think extra negative voltage power supply for the grid, and no resistor, or maybe a tiny resistor, between the cathode and ground. Okay, high voltage at the top, like 250 volts at least, maybe as much as 500 volts. On the left, we're putting in a signal with an amplitude of around 10 volts or so. And at the plate, that signal is amplified to an amplitude of around 100-ish volts or more. Wow! Now what's up with that coil of wire on top of the plate? That's half of a transformer. So let's draw in the other half and where it goes. That's your speaker. So on the tube side is a high voltage, low current signal, and on the speaker side is a low voltage, high current signal required by your speaker. In a nutshell, that's a single-ended output. And push-pull? That's harder to draw if I want to keep higher voltage at the top, never mind signal going from left to right. I'll draw it first with high voltage at the top. You will never see a push-pull circuit drawn this way, but let's go with it for now. You can see that we're hanging two coils from the high voltage, and we're driving current through two tubes. Now, if we fed the same signal into the grids of both tubes, the amplified high voltage signals in the coils would cancel each other out. And what would be the use of that? Instead of making a silly, stupid, no-good amp that makes no output, we feed the two tubes with opposite signals. Instead of the tubes pushing against each other or pulling in a tug-of-war, one tube pushes while the other pulls and vice versa. I'll redraw it in a way that makes the push-pull aspect clearer and maintains the signal goes from left to right convention, but violates the high voltage at the top convention. Instead, we'll put the high voltage in the middle, and I'll show the opposite signals. Going into the two grids on the left. While the signal going into the top tube is on the upswing, the signal into the bottom tube is on the downswing, and vice versa. This scheme has distinct advantages. First, the output transformer doesn't need to tolerate a constant one-way direct current, just signal current, so the transformer doesn't need to be as big as for a single-ended amp. The second big benefit is that the undesirable signal, or ripple, in the high voltage cancels out, whereas the ripple produces an audible hum in single-ended amps. This configuration does introduce some problems, though. First, it does make things more complicated. We have to include a signal inverter ahead of the output stage, to get the opposite complement to the non-inverted signal. Second, the push-pull circuit cancels out even harmonic distortion, which is generally pleasant sounding, and doubles odd harmonic distortion, which doesn't sound good. Push-pull amps therefore need a lot of negative feedback to correct that odd harmonic distortion. And we've got to be persnickety about making sure the signals are both equal and opposite. People will tell you that push-pull circuits also introduce nasty crossover distortion, but real amps are generally designed so that crossover distortion doesn't kick in until the amp is driven into clipping. Hey, guitar people, you're complaining that you want to overdrive the amp. You want that sweet, soft clipping that tubes do. Yes, and you can do your clipping prior to the output stage. Okay? Okay. Now, I said that push-pull amps need an extra thing to provide an inverted signal to one of the tubes. But let's back up further and see what else we need for the simpler single-ended amp. Generally, we need a gain stage upstream of the output stage. Okay, so I'll draw the output stage again. So here. So like we have high voltage here, we've got high, but not so high voltage here. Looks just like the output stage, except it's got a resistor between the high, but not so high voltage and the plate. But what's wrong with this picture? Remember how I said that we want 0 volts DC on the grid of the output tube? But here I've gone and hooked it up to high voltage. So we need a DC blocking capacitor in the middle, here. This is sometimes also called a coupling capacitor. Yeah, I know. Blocking and coupling sound at odds with one another, but blocking is what it does to DC, and coupling is what it does to AC. It blocks the high DC voltage from reaching the grid of the output tube and allows the signal through. Now back to push-pull. Again, I'll draw the output stage with high voltage in the middle. It also needs a gain stage, so I'll put that on the left side. In between, we need an inverter, or a phase splitter, which I'll draw as a so-called split-load inverter. There are other types, but I think this one is the simplest. We work it so that we get unity gain at the plate, and we also take the unity gain signal from the cathode. Of course, we'll still need blocking/coupling capacitors. If you know your tube circuits, you'll notice that I've left a lot out of these simple sketches. For those of you who don't know tube circuits, I've left out some important bits. Okay? Okay. In my eagerness to get to the gain and inverter stages, I left out an important advantage of the push-pull design. We get more than double the power out. That's right. Say our output tube of choice is an EL84. In single-ended, we get about 3 watts. With 2 EL84s in push-pull, we get about 10 watts. How does that work? Don't worry about it. Just accept that it's true because it is. If you must know, it's that we get about double the voltage swing, and power goes as voltage squared. It works out. Trust me. Regarding the relative merits of single-ended and push-pull designs, I said that push-pull allows smaller output transformers than we'd need for similar power in single-ended. I said push-pull eliminates hum from the high-voltage supply, and we get more than double the power by doubling the tubes. On the downside, we need an inverter, and we need negative feedback to get rid of odd harmonic distortion. If you want an amp with even harmonic distortion, then push-pull is bad for you because the push-pull configuration cancels out even harmonic distortion from the output tubes. And the negative feedback needed to eliminate odd harmonic distortion also eliminates any even harmonic distortion introduced by the gain and inverter stages. Oh well. If you just want a nice amp that has low distortion and no hum, then push-pull is the way to go. You can certainly use negative feedback in a single-ended design, and you'll definitely want to if you're using pentodes, as pentodes, in the output stage, because pentodes mainly produce yucky odd harmonic distortion. I mentioned the big pro of push-pull amps being that you can get over double the power of a single-ended amp. I also mentioned that with push-pull amps you could use smaller iron, implying that with single-ended amps, at least the best single-ended amps, you need pretty big iron. And so, single-ended amps, even really good ones, tend to be pretty low power. Like a single-ended 300B amp, that's going to be like 6 watts. Whereas the Dynaco Mark III push-pull KT88s, you can get 60 watts per channel. So with push-pull and decent-sized iron, you can get quite a bit of power. Whereas you need mondo, humongous iron, and a huge mondo radio transmitter triode to get a lot of power with a single-ended triode amp. Any other pointers for potential consumers? Look at the iron. Single-ended amps can be pretty good without big iron, and push-pull amps can get by with smaller iron, but the best of both types use big iron, and by big, I mean that the output transformers may be as big as the power transformers. I'll show you an example. This is a Dynaco Mark III. Power comes in here, so I'm assuming this one is the power transformer, but to be perfectly honest, I can't remember. But if you'll see, the sandwich for the output transformer here is actually bigger than the sandwich for the power transformer. And they're both of similar size. Geez, the output transformer might even be a little bit bigger. This sucker can produce about 60 watts per channel with these push-pull KT88s. And it is friggin' heavy. Whew. Iron that big isn't necessary for a good amp, but small iron isn't sufficient for the best amp. Just know that the best amp will cost you. Ask questions and expect answers. What are the amp's limitations? How much of its full power is clean down to 40 hertz and below? If it's a 10 watt amp, does it make a clean 1 watt down to 40 hertz? 3 watts should get you a half. 100 watts should get you 10. The best 10 watt amps will get you 10 watts at 1 kilohertz and 40 hertz, maybe lower. If you look at an amp with small iron and the maker claims full power down to 40 hertz, you should ask for and expect data, preferably from a third party like Amir or Steph at Audio Science Review and Skunky Designs, respectively. Don't just believe that the maker has found a loophole in the laws of physics. A certain mass of iron simply will saturate at a certain amplitude of low frequency. There's no magic flux container. Again, so I'm clear, amps without big iron may be worth your time and money. The maker should just be honest about the limitations of those amps. I've sold amps that don't have big iron. I make sure the buyers know the limitations of those amps. Hell, I demonstrate those limitations. I personally enjoy those same amps, but I don't expect what they're incapable of. Look inside. Ask about what components the maker used. You should expect capacitors with reputable name brands: Rubicon, Elna, Nichicon, Wema, TDK, Panasonic. If you're paying top dollar for a vintage tube amp, you should expect new electrolytic and film capacitors. Be wary if the seller claims the amp is more valuable because those capacitors haven't been replaced. All original capacitors in a 60-year-old amp is not a good thing. Rather, all original is practically a guarantee of catastrophic failure in the near future. Old paper-in-oil coupling capacitors are likely to fail in their job of blocking DC voltages from the output tube grids. Red plating is the eventual result. Those paper-in-oil caps are dangerous. What about new oil-filled capacitors? What about high-dollar film caps? I'll use expensive film caps in speakers where precision and materials matter. Still, I don't go with the most expensive ones. And high precision in capacitor values usually isn't necessary in amplifiers. Phono preamps are another matter. Why don't I use, say, Mundorf capacitors? Because I'm not going to spend that kind of money without evidence that the cost provides the promised benefits. I'm not going to spend $100 on a capacitor when the maker doesn't even provide a data sheet. How gullible do they think I am? Now, if you want to commission an amp from me, want high dollar caps, and pay for them up front, I'll happily do what you want. And I'll use WEMA film caps in the amp I keep for myself. I'll mention a couple of things I don't think you should expect from tube power amps. Front panel power switches and rear panel input jacks. I generally put the power switches on the back next to the power transformer. I don't want to have wires carrying lots of alternating current crossing back and forth across signal paths in my amp. I want to keep the power supply circuit confined and as far away from the signal circuitry as possible. You want the best sound and will pay top dollar, but you can't reach around the back to turn the amp on? Or use a power strip as a master switch? An amp should have an on-off switch on the front. Please. It really shouldn't. Similarly, I don't want my input signal going back and forth over great distances inside the amp. Let it cross the amp outside the chassis, which is metal and has a metal bottom, so the innards are contained within a Faraday cage. If you don't like the look of the cables near the front, then buy more attractive cables. There are some nice ones on Amazon for about $20, but I don't want to get into a debate about cables right now. If you found this video useful, please give me a like, a subscribe, comment. What have I gotten wrong? Must have gotten something wrong. Have a great day, and I'll talk to you soon.